What if some of the most familiar features of our world, like space, time, or gravity, are not built into reality, but emerge from something deeper? What if they are more like the shadows the prisoners saw on the walls of Plato's cave than fundamental parts of the universe? For centuries, physics has been our way of stepping outside that cave. But what if even our fundamental laws are still just shadows of a deeper truth? In physics, the concepts of fundamental and emergent sit at the heart of this mystery, and we will start to unfold it by explaining them. A fundamental property is like an unbreakable Lego brick of the universe. It's something built into the rules themselves, indivisible. Think of Planck's constant. The electric charge of an electron, or the speed of light, for instance, they are all fundamental. These are the instructions in the cosmic rulebook, printed in ink we don't yet know how to erase. An emergent property, by contrast, appears when many fundamentals interact. It doesn't exist in a single piece. Temperature, for example, doesn't exist in one lone atom. It only emerges when countless atoms move and exchange energy. We see this in everyday life too. Traffic jams emerge when thousands of drivers interact. Waves in the ocean rise and fall, not because water knows the plan, but because countless water molecules push and pull on each other. Fundamental and emergent are opposite concepts locked in a tug-of-war over what is truly real. And sometimes, figuring out what's truly fundamental isn't just a technical detail. It can turn physics upside down. That's exactly what happened in the 1970s with black holes. Black holes were once thought to be the ultimate fundamental objects, regions where gravity rules everything and nothing could escape. Then Jacob Bekenstein noticed something strange. Black holes seemed to have entropy, a measure of disorder, and it depended on the surface of the black hole, not its volume. That was bizarre. Stephen Hawking set out to prove Bekenstein wrong. At first, the math seemed on his side, but then it betrayed him. His equations said black holes weren't perfectly black at all. They glowed. He found that black holes must emit radiation, now called Hawking radiation, meaning they had a temperature. And temperature means microscopic degrees of freedom of something. But what? What could be moving freely close to a black hole? This was one of the first hints that spacetime itself might have hidden underlying parts, and that gravity might be emergent from them. Hawking later said that it was the only time a calculation had made him physically sick. Because if black holes, the ultimate symbols of fundamental physics, hide emergent details, what else in the universe could be shadows rather than the source? In science, labeling something as emergent is powerful. It says this is a shadow, not the object, a consequence, not a cause. In the 19th century, scientists believed heat was fundamental, a kind of invisible fluid called caloric. Then thermodynamics and atomic theory revealed it as emergent motion of particles. In the early 20th century, time was thought to be absolute, the same for everyone. Then Einstein showed it was woven with space into a flexible fabric called spacetime, bending under the influence of gravity. Now, in the 21st century, we may be witnessing the next downgrade, the idea that spacetime and gravity themselves are not truly fundamental. In some modern theories, they're emergent, arising from more basic ingredients we have yet to fully uncover. Theories now on the frontier of physics treat even spacetime as emergent. The holographic principle, proposed by Gerard de Hooft and Leonard Susskind, inspired by Bekenstein's and Hawking's work, says all the information in a region of space can be described by data on its boundary, like a cosmic hologram. Imagine a universe where everything you see in 3D is actually encoded on a distant 2D surface. Our reality would be more like a hologram than a solid object, and if that's true, maybe our whole 3D world is just a projection from somewhere else. A DS/CFT correspondence, Juan Maldacena's 1997 breakthrough, gives a mathematical example of the holographic idea. A universe with gravity is equivalent to a lower dimensional universe without it. It's like a video game. The game looks 3D while you play, but behind the scenes, it's made from 2D code on a flat screen. Mark van Ramsdonk showed that in holographic models, quantum entanglement actually stitches space together. Even far apart, entangled particles act as if they were linked. In these models, those invisible connections are like the stitches holding the fabric of space in place. Remove entanglement and the geometry dissolves, which raises the question, is space itself just a giant web of invisible relationships? In Erik Verlinde's Emergent gravity theory, gravity and geometry aren't fundamental. Geometry is something that forms from an even deeper layer of microscopic information, a bit like how a hologram's 3D image emerges from patterns on a flat surface. Gravity, in this view, is the large-scale effect of those hidden information patterns shaping the geometry we see. These ideas don't just tweak the rules, they suggest we might have been studying the shadow all along. All of this matters because classifying something as emergent changes how we search for answers. If spacetime is emergent, the ultimate theory of everything won't be found by simply quantizing gravity. We'll need to look at the deeper, pre-spacetime reality that generates it. History shows a pattern. Earth isn't the center of the universe. Atoms aren't indivisible. Space isn't fixed, and gravity might not be fundamental. As we learn more, the foundation shifts. So if gravity is a shadow, what's casting it? According to the emergent gravity theory, the object casting the shadow is the microscopic information structure of the universe, essentially the quantum bits of spacetime itself, shaped by entropy and thermodynamics. Gravity, in this view, is just the large-scale pattern that appears when you zoom out far enough. In string theory and holographic models, the shadow comes from a higher dimensional reality. Gravity, as we feel it in 3D space, is a projection, like a 2D shadow of a 3D object, from deeper geometric structures, or even an entire universe encoded on a distant boundary. And in quantum gravity ideas, the shadow might be cast by entanglement networks at the smallest scales, where the shape of space-time is literally built out of quantum relationships. In Plato's cave, prisoners thought the shadows on the wall were the whole of reality. Only by stepping outside could they realize the shadows were cast by something far greater. For centuries, we've stepped into new light again and again, from Newton's clockwork universe to Einstein's flexible spacetime, and now, perhaps, to something even deeper. If gravity and spacetime themselves are only shadows of a more fundamental truth, we may be standing at the mouth of another cave, ready to step into a brighter, stranger world. Will we even recognize it as reality? The universe's complexity may be bigger than we thought, but deciphering it may well bring a new world of possibilities. Thank you for watching. If you want to uncover more hidden truths about our universe, subscribe and step further into the loop.